Welcome, everyone. Our speaker today is Daniel Krenn from the University of Salzburg in Austria, and he is going to speak to us about k-recursive sequences and their asymptotic analysis.
Okay, thank you. I will start with what motivated this research, and that's a problem or question on something called unbordered or bordered factors of a word. And I will start explaining, and then during explaining, also tell you what the question of interest for me will be and what motivated exactly this study. So let's start directly. A word is called bordered if there is a border on the left and on the right. So meaning there is the same subword on the left and the right as a prefix and a suffix, so to say, and otherwise it's unbordered. Let's look at a couple of examples. 0, 0 is bordered because there's the 0 left or on the right, 1, 1 with the same argument. 0, 1, 0 is bordered because there's the 0 there. 1, 0, 1, 0. Okay, it's on both sides. And also here, 0, 1, 1, 0 is here, and 0, 1, 1, 0 is here. So that's border of a word, and we exclude kind of trivial cases and so on and so forth. The word is called unbordered if that's not the case, and here are some unbordered words. So I'm looking here at the binary sequence of letters. So 0, 1, so single letter words are unbordered. You see here there is nothing that could be a border there, and so on and so forth. All these examples are presented are substrings or factors of the 2 Morse sequence. I guess many of you know that. Very briefly, it's this infinite sequence here. One possible way to describe it is you start with a 0, and then whatever you have, you kind of mirror in the sense that you flip zeros and ones and add it. So if you have a 0, then you add a 1, then you have 0, 1, and you add 1, 0. You have 0, 1, 1, 0, you add a 1, 0, 0, 1, and so on and so forth, and you continue with that construction. All these examples are substrings or factors, so to say, of the 2 Morse sequence. What is okay, that's the first thing. Here I've written down the length of these factors, and what's of important for this talk will be the length for such factors if there is a certain factor of that and that length, or more to be precise, how many unbordered factors of a certain length there are. Here are given all the unbordered factors of length up to 3. It's not easy to check because we have an infinite word here, so it might be that something appears later on, but in fact these are all. How to check if some word is there, or what can we say at least to what is known on unbordered factors? We have this result here. So the question, is there an unbordered factor of a certain length in the 2 Morse sequence? The answer is take that n, write it in binary, and check if it satisfies this regular expression or not. So if it's not of that type, then there exists an unbordered factor of that length. So that answers the question on existence for a particular n. The number of unbordered factors of a certain length, here is the list of the first 16 terms given. You see here 1, 2, 2, 4, 2, so it kind of fluctuates up and down. Yeah, we have this sequence here. And that will be the sequence of interest for me. In particular, I want to know what can we say asymptotically on this sequence. So if n gets larger and larger. And we will see as this fluctuates quite heavily, we'll focus on the summatory function of this sequence, meaning building the partial sums of the first n terms, looking what can I say of this new sequence. That kind of has an averaging effect as well. So you can see it also as an expected value in some sense. There are a couple of things known for this sequence. It grows at most linearly. To be precise, it's always small or equal to n. It holds, also equality here holds infinitely often, and that means this limit superior here, this quotient equals 1. So that's at least some result on what you can say on the asymptotic behavior. This is one part what is known on this sequence. Of course, there are many other things known. The other thing is how to compute such values. And there is a nice recursive description. We'll also give you that here, because that will be of quite importance now. We have this kind of description of the number of unboarded factors of length n in the 2-Mose sequence. On the left-hand side, you see here some 4n plus something, or 8n plus something. And on the right-hand side, you see finite sums of subsequences of that sum. And here we have, again, 2 to the something times n plus something. The title of this talk includes k-recursive sequence, and we now slightly rewrite that set of recurrence relations, and what we will then get, we will call a recursive sequence, namely in the following way. We get rid of this force here and try check if we can do it and rewrite it that we had 8 times n plus something. All the time we have the something is all the residues mod 8, and 8 is for this particular example, of course, the case. And on the right-hand side, we check if we can rewrite it so that we have here always the same factor. Indeed, it's possible to be able to rewrite it with a 4 here. I go back once more. What we simply have to do is, okay, here insert 2n, then we have already this equation for the 8n here, and here we have to do some insert 2n plus 1 and do some proper substituting. So it's not a hard task to do that. It's simply you just have to play a bit around, then you get that. That's exactly what we call the 2-recursive sequence. Now I will give you the precise definition in a moment. The question is, once we're having a sequence that falls under such framework and has this kind of shape, can we do asymptotic analysis of that sequence? The answer is yes, because we can do it much more generally. But in that particular case, when we have this kind of type of sequence, you can basically use the information on the coefficients you see here more or less directly to go into asymptotics. And that's what makes these sequences so nice to look at and so good to understand in some sense, at least. Okay, so 2 recursive sequences, or in general k-recursive sequences, actually, so I slightly changed the title of the talk. In the title there was q-recursive sequences, and now I'm switching to k-recursive sequences as I decided to use that letter here for this talk. Nevertheless, so what's a k-recursive sequence? And now look here on the right-hand side. That's the recurrence relation that we had before. So we have a sequence x. We have here k to the something, that was the 8 that we had before, plus the s, so that the residue class is mod 8. Sorry, the residues mod 8, not the residue classes, sorry. So we have here a subsequence, and that subsequence can be represented as a finite sum of here some coefficients and here some other subsequence, k to the m is small, the small m is smaller than the capital M, plus some j that does not need to go through all residues mod something. Just assume that it's bounded by some constants. So whenever I can write all these subsequences as these finite sums here of, well, these subsequences appear here, then we call it a k-recursive sequence. And what's here on the left is just all the parameters that are here inside, and the corresponding quanta is an existence quanta. So all these parameters have just to exist. So that's the case. Let's look at some examples. One of the simplest non-trivial examples is the sequence H here. The largest power of 2 that is less than or equal to n. So having a number and searching for 2 to the something that is smaller or equal to that than that n. So if n is a power of 2, then of course that's the number, and otherwise taking the next smallest one. That sequence has a recursive description of that type, the h of 2n. So if I double a number, then that power of 2 will be also just multiplied by 1, or the power will be increased by 1, depending on what we say. And adding 1 doesn't change anything, so still the doubling here. So we have a two recursive description within that framework. So K2, here the parameters m, l, u, and the n0. It's from which n on it's valid. So we have one example here. The binary sum of digits does not fall under this framework, at least not directly, so to say. So binary sum of digits, meaning taking a number, writing it in binary, and then summing up the digits, meaning counting how often there is a 1 for the binary. If I multiply that number by 2, then that stays the same. If I multiply by 2 and add 1, then there comes an additional 1, so the sum increases by 1. So that's the recursive description. And due to this +1, it doesn't fall into this scheme here, because not be able to have an additional 1 here. That's at least a direct consequence of this definition. On the other hand, I can overcome this in various ways. One way would be to use a different recursive description of the binary sum of digits function. So that is available, one that has some sequences here instead of the 1, so subsequences of the S here. So that works out. On the other hand, I can even, so within this framework of k-recursive sequence that I will present you, or I'm currently presenting you, I can deal with inhomogeneities like this here. That's in the corresponding paper. I will not go into details for this talk, but that can be dealt. Basically, you have to kind of increase these exponents here. So you have here 2 to the 1, that has to be increased slightly, so in order to deal with such sequences. Okay, for the binary sum of digits, and of course, our original motivation, the number of unboarded factors of length n and the 2 or more sequence also falls under this framework. We've seen it before, this kind of recursive description. Quite closely related in some sense, but also slightly different, is the concept of k-regular sequences, as many of you in the audience know very well. And indeed, there's a connection between these sequences and the k-regular sequences. So a brief reminder on what k-regular sequences are and what the differences are now. We again have subsequences here written as a finite sum of sequences. Okay, coefficients are still there as before. Now these finite sequences can be any sequences. Before there were exactly subsequences of our original sequence, although that doesn't really matter much. So there are other descriptions as well here, but in that sense, that's different. In that sense, that's more general. And here, before we had a fixed power of k, we had k to the m. Here over the residues, mod k to the m. Now we allowing j, or have to satisfy that condition has to be satisfied for all possible j. So meaning here we have a much stronger condition in the sense there are much more sequences that we have to check, or where such a description has to be available. If that's the case, then we call such a sequence a k-regular sequence, and there is a more fancy way to formulate that. The k-kernel is the set of all such subsequences that has to be contained in a finitely generated model. So that's one possible way to describe k-regular sequences, but it's not the only possibility, because equivalent to that definition, there is the way to saying that a k-linear representation of the sequence exists, and I will also explain you that, because we will need that quite heavily then for our k-recursive sequences. Let's go for the moment to the binary sum of digits function that is in fact a k-regular sequence. We had these recurrence relations that you have just seen before. Let's rewrite that in a vector valued form. here, we take the sequence and we take the constant sequence 1, because it appears here, and try to rewrite that system of recurrence relations in that vectorial form. The vector of 2n is just, okay, our sequence of 2n is equals sequence of n, so we have the identity here, and our constant sequence stays the constant sequence, so it's here as well. Here, for the odd numbers, we have again the constant sequence that stays, and for the for the odd part here, we have to add the one, so the 2 ones here, we just add in. Okay, the only important part is now, when we have such a description, then we can rewrite it in vector matrix as a vector matrix multiplication, and we can iterate that process, meaning I have a number, check whether it's even or odd, then get a new number. Again, check whether even or odd, and get finally the digit expansion of that number. But for each digit on the other side, I get a matrix. And so what we end up here is kind of a product of matrices. And indeed, it turns out that that is equivalent to being a k-regular sequence. Namely, if there are k-square matrices M, here these two, some initial vector at the beginning, and then I end up with a vector-valued sequence, and I want a single-valued sequence, so I have to extract that. So it's the other vector on the other side. And if I can write all terms of the sequence in that shape, then it's called also k-regular, equivalent to that. Meaning, taking n, write it with the k-array expansion, and for each of these digits, take the corresponding matrix. Examples of k-regular sequences, so the binary sum of digits already mentioned. The largest powers of 2 less than or equal to n is again an example of a k-regular sequence. This is not a surprise. I'll also tell you in a moment. Here, 2 to the j times n doesn't change anything if there's here 2 or 2 to the j as we had before, because it's just if I multiply by some power of 2, I just can pull it out. And here +1 or plus something that is smaller than the 2 to the j also doesn't change the power of 2 that I'm considering. And now, what's the relation between the k-recursive sequences of this talk and the k-regular sequences? And indeed, it turns out every k-recursive sequence is indeed k-regular. And another important point is the k-linear representation, which every k-regular sequence has, or has a nice structure, namely a nice block structure that is either on this vectorial form and also on the matrices that are kind of block matrices. We will see this kind of block structure later on when we deal with the examples, and then we can kind of see what the really nice structure of them is. It will indeed turn out that that nice block structure helps us in doing asymptotics, and that's in particular nice for the k-recursive sequences. As said here, we can compute the coefficients quite easily out of the k-recursive sequence. So basically just taking the coefficients out and compute the coefficients of the matrix. And there are even explicit formulae for the rows available of these matrices. Okay, so let's go back to the unbordered factors. We had here this system of recurrence relations. We do as a first step, now we are in the process of getting this K2 linear representation in that case, for that case. We first extract the coefficients. That's, yeah, nothing mysterious happens here. So I just take the coefficient here. You have the 2, so it's the 2 here. I have a 1, and here shift 1 here, so I have a 1 here. 1 and 1, 1, 1. So really nothing mysterious happens here. -1, 1, +1, 1. It's just for some reason I split up here. It will turn out that that's exactly the correct way to split it and the correct way to look at these matrices. So from this point on, from this system, we have extracted these 2 matrices, and we now continue getting a 2 linear representation. Here is one given for this particular example. I have these 4 lines already here from before. These correspond to these matrices B0. And then, in some sense, I just have to add two matrices here on top that have entries 0 and 1, and they are quite easy to understand. They have. Before I talk about some details on these matrices, we kind of repeat this step in some sense, because these system of recurrence relations were only valid from some certain n on, I think from n up to 4 or something. We want from n to 0 on, so we have to deal with these initial values. We can do that quite easily and get kind of a larger linear representation of the numbers. Here, the matrices are M. They appear again here. Again, some J matrix with entries 0 and 1. And here, something that deals with initial values. The important part now is when we're starting from a k-recursive sequence, we always can write the linear representation in these ways. And when you look at these block matrices, we have a kind of block upper triangle structure. So there's the 0 here, and that will happen also here. And that helps us in the asymptotics then, because at the asymptotics we have to extract eigenvalues and all kind of other stuff from these matrices. And due to this block structure, we can extract it from each block separately, so to say. And it will indeed turn out that this block here, where there's only 0 and 1 entries and quite nice matrix, usually does not influence the asymptotics at all, because they are kind of too small and everything goes in the error term. Of course, we have to check that that's really the case, but indeed, it usually turns out that the only relevant part comes from these matrices B0 and B1. And that's in particular nice because all these kind of transformations that we have to do add additional lines or entries in the matrices and make them larger and larger, and therefore computationally more hard. I think I even have given it here. So we end up after here with a matrix of dimensions, or with a two linear representation of dimension 10, and by a minimization algorithm we can reduce it to at least dimension 8, compared to dimension 4 that we have here with the B matrices. Okay, so at this point, we're now at the end of the second part. Just remember, these B matrices come from the k-recursive sequence, from the recurrence relations directly from the coefficients, and that are the only part that is basically relevant, and all the other parts are, at least for the asymptotics, usually irrelevant. So that's the important part, and that's what makes these k-recursive sequences so nice. Okay, so now I've talked a lot on, or I mentioned already a lot of times the asymptotic part. So let's go into the asymptotics right now. At the beginning, quite generally for k-regular sequences. So if I have a k-regular sequence, I want to look at the asymptotics of the sequence, or in that particular case, the partial sum sequence, summing up the first n terms. For the asymptotics, I'm using that result here because it gives you some additional information on these fluctuations. I'll tell you in a moment. So first, when you see this, just one or two steps back and zoom out, and let's see the bigger picture here. We have some asymptotic formula, main terms and error term. And then there is some description on what nice things we can say about these parts here, in particular these fluctuations. In particular, we get for this function, for the corresponding Dirichlet series, a functional equation that is quite explicit, that helps to get additional information on the sequence or on this fluctuation, so to say. We know analyticity properties of these functional equations, so where the poles are and so on. We can even compute residues of this sequence, of this functional equation at certain points. And that's exactly what one needs to understand these fluctuations, so to kind of extract the Fourier coefficients out of it. And indeed, it turns out we can compute Fourier coefficients quite efficiently via this approach. So not needed to kind of understand the details right now, just there, look at that formula. It's quite explicit, and that's what makes it nice. A bit more closely, let's go into this formula here. The outer sum is a sum over eigenvalues. So sigma is here the spectrum of the sum of these matrices from a linear representation that we had before. And each eigenvalue gives us someone here. N to the log of that eigenvalue is the growth of this term. Almost at least. There might be an additional logarithm if some multiplicities appear here in the spectrum. And then there's an additional function phi that is this one periodic continuous function, and even we know more on the Hölder continuity of this function, and so on and so forth, and can compute Fourier coefficients. So each main term looks like this, meaning there is some growth and then there is some fluctuation. And there is some error term. The error term has here capital R that's closely related to that rho. The rho is the joint spectral radius, and the capital R is usually the joint spectral radius. Sometimes it needs to be an epsilon larger than that. I will tell you on the joint spectral radius in a moment. It's not that important for that talk, but I will go briefly into it in a moment. So what we have looks like, or is quite a very explicit description of the asymptotics of such functions. And in fact, it can be applied to all k regular sequences. That's on the plus side. On the minus side, it might be that the result doesn't give you much, because it could be that that error term here gets so large so that no other term here appears or is still there, not eaten up by the error term. In fact, if you would do this analysis for our original sequence, the number of unboarded factors, not the partial summing, then that would be the case, so that the error term would get too large and we don't get any result out of that. On the other hand, if you're doing partial sums, we will see that that works out quite nicely. So very briefly now, how to get the asymptotics, what we need to do. So we need to compute here the eigenvalues and the joint spectral radius and put everything together. I've did that with the binary sum of digits function, and let me walk you through this process quite briefly. We add the two matrices that we already had seen before, compute eigenvalues, so it's eigenvalue 2 with multiplicity 2, or we can see here the two 2's. We can compute the joint spectral radius is 1. On the next slide, there will be a formal definition. And now from that information, we can already determine the shape of the asymptotics, because we have 2 here. So compute the log to base 2 of 2, that's 1. So that's why we have an n to the 1 here, and an n to the 1 here. Multiplicity is 2, that's why we have 2 summands here, one with log n and one without the log. And both have some fluctuation. Usually there should be an error term. It can be shown by slightly digging into the eigenstructure that that error term is not present for the sum of digits function. So no error term here, just, yeah, we have to dig into the eigenstructure here. Just slightly, not much. There's a simple criterion for that. It further turns out this fluctuation in the first term is not actually fluctuating. It's simply constant 1/2. Get that via the functional equation. And there's still left this fluctuation here, where we can compute Fourier coefficients quite efficiently. And what's left is this result, the classic result of Delange for the binary sum of digits function. Main term 1/2 n log n, so that's what one would expect. And then there is an error term order n, or not an error, next term of order n, and that's fluctuating. So that's the process, what we have to do. There is some detail hidden here with the joint spectral radius, because that's not always that easy to compute. First, what is the joint spectral radius? We take products of matrices of length L, take a norm, any norm suffice, so that's all gives the same joint spectral radius, normalize it, and then the maximum of all these, and then taking the length longer and longer and longer and longer. That limit always exists, so that can be shown, and that's the joint spectral radius. So the spectral radius of a single matrix says something on how powers of this matrix grow. The joint spectral radius tells you something on how products of matrices, now with more matrices, grow. For the binary sum of digits function, it can be computed quite easily. You need some upper bound and some lower bound. So looking at the eigenstructure here, and then proper norm here, the maximal spectral norm, then everything is easy in that example. But usually that's not the case. But at least there are approximation algorithms available, although computationally finding the exact result is hard. Okay, now that's the process of asymptotic analysis on k-regular sequences. Let's look at our example of the unbordered factors. Remember, we had these two matrices here. And I mentioned already that basically the asymptotics depends on only these matrices and not on the full K2 linear representation. That's what this note here says. So only these properties are relevant. What do we need to do? Compute the spectrum. Okay, it's quite straightforward to do. Compute the joint spectral radius. It's not that easy with these matrices, so at least not directly from viewing them. You have to do a proper transformation or using a proper norm to see that. But indeed, it can be shown that that is 2 here. And with that information and that we have something that's called the simple growth property on these matrices, meaning that influences how the error term is handled, we can already write down what the asymptotics of our unbordered factors looks like, the summatory function. It will be, okay, here we have 2, so in the spectrum, only eigenvalues that are larger than that 2 are relevant, so that's only 1 plus square root of 3. And here's the result. So, summatory function of our function, and to the kappa is exactly 1 plus square root of 3, taking the logarithm of 2, so that's that constant here, some fluctuation here, and then some error term that depends on the joint spectral radius. So we have n to the log 2 of 2, because the joint spectral radius is 2, so that's the one here, and an additional logarithmic factor because 2 is also in the spectrum. That's I need one additional factor, a logarithmic factor. And we have all nice properties from before. We have that's a one periodic continuous function. We know something on the Hölder continuity of that function with the exponent. We have an explicit functional equation for the corresponding Dirichlet series. We have analyticity properties. We know a lot of the on the poles of this functional equation, and so on and so forth. So we can efficiently compute Fourier coefficients. And indeed, down here is the fluctuation phi f plotted. When I remember correctly, I think something on the roughly on the first 2000 Fourier coefficients are taken for this representation, and they can be just computed quite easily. Okay. At this point, we have now answered our original question on the unbordered factors. So what can we say on the asymptotics on that? And that's basically it. We have seen that we kind of could have used this framework of the k-recursive sequences. Now, let's hope that that framework is a framework that can be applied to other sequences as well, and doing nice and easy asymptotics there. And indeed, that's the case. I will present 2 more examples in the last part of the talk. So the first is Stern's diatomic sequence. Sequence is defined as follows. If I multiply it by 2, then it stays the same. And if I multiply by 2 and add 1, then we add these 2 up, and there are some initial values. The first 16 terms are given here. And indeed, this sequence appears quite frequently, and also check who's in the audience, but many people in the audience, I guess, have already worked with that kind of sequence. We have that. So some examples here where this sequence appears. For example, the number of different hyperbinary representations. So meaning base 2 and digits 0, 1, and 2. How many representations does a number have? That's the answer is this kind of function here. Stirling partition numbers, how many are there that this term is even and non-zero? It's also this sequence coming out here. Number of different representations as a sum of distinct Fibonacci numbers with even index. Also, that is counted by that number here. I think it's d of n+1 when I remember correctly. Number of different alternating bit sets, whatever an alternating bit set might be. There is a formal definition of that. Also, that is counted here, and then there's a relation to the towers of Hanoi. So it's really a sequence that appears quite frequently. And what's now important for this talk, it falls under that scheme that we had before. We have a 2 to the 1 here, all the residues plus 0 and +1, mod 2. And here we have 2 to the 0, all these kinds. So we can apply our framework, and indeed, asymptotics falls out of that quite easily. Just work out the details, meaning compute the eigenvalues, compute the joint spectral radius, and you get that result. Again, as explicit as before, so we have summatory function, we have here some main term and fluctuation, some error term. We again know on this fluctuation basically what is there to know. So continuity function, and we can compute Fourier coefficients again quite easily and efficiently. Here the fluctuation is drawn. At the end of this talk, I will show you that it's also possible to get rid of this error term here with a slight modification here. To do that, we need to go to a different sequence and then kind of link that back to that sequence here. That's now the last example I will present with a bit more details, as they might be quite interesting, and we will see how we can walk through this process of asymptotic analysis with k-recursive sequences again. Generalized Pascal's triangle, one possible generalization. Also here, some people are in the audience that worked already with that and have written very nice papers on this kind of stuff. So for the classic Pascal triangle, there is a binomial coefficient each entry. Here we extend that to a binomial coefficient of words. Basically, you take two words and look how often the one word appears in the other word as a scattered subword, meaning it doesn't need to be, the letters do not need to be consecutive, but they can be distributed somewhere. But the order doesn't need to stay the same. It's not allowed to change, that the order is changed. We'll show you the triangle, Pascal's triangle in that case here, and then we'll start with an example. One example, for example, could be that entry here. So the U is 1, 1, 1, and the V is 1, 1. And we have to check how often this 1, 1 can appear here in the 1, 1, 1. And there is the way the first could be first here. If so, then the second could be the second or the third. So there are two possibilities. Or the first could be the second one here, and then the second here has to be the third here. So that's one possibility. That's why we have 3 here. Meaning, okay, 2 ones here, 3 ones here. So the classical binomial coefficient, I have to choose 2 out of 3. And indeed, the classical binomial coefficient is exactly this. So if I only look at the ones, then I get the classical binomial coefficient. They are marked here in green. You might see them as well. For this talk or for this example, we will be interested in how many entries in each line are non-zero. That's the number set of n given down here. And we want to do asymptotics of that, or at least of the summatory function of that function. Briefly zooming out, well, that's a nice picture of these non-zeros in this triangle. Counting them is possible, and asymptotics can be achieved in various different ways. One is via this theorem. It connects these number of non-zeros in Pascal's triangle with a Stern's diatomic sequence that we had seen before. There are the entries in there. We know in the asymptotics there, so we can say something on the asymptotics there. basically done. But as I mentioned before, we want to get a bit more into details and get something out of that, because still there is this error term there that shouldn't be there, because it's possible that we have an asymptotic result without the error term, as we had it for the binary sum of digits function. There's also this result. It has a recursive description, namely this set of recurrence relations here. Again, 4, 4. Okay, here's 2, so we slightly need to rewrite that. Plug in 4n plus something. Oh no, sorry, 2n plus 2n and 2n plus 1, and then getting different set of recurrence relations. So let's do that and get again a 2-recursive sequence, slightly rewriting that. Look at our coefficient matrices, now 2 by 2 matrices, quite easily, just giving the coefficients there, just read them off. That leads to a 2 linear representation, then of dimension 3. So we again have to add these 0, 1 matrices that for asymptotics do not play any role. We can again kind of minimize that and finally get to something of dimension 3. We investigate for the asymptotics, compute the spectrum of the sum of these matrices, compute the joint spectral radius of these matrices. We need to slightly go into the 2 linear representation now to see that there is indeed no error term. But it's also not hard. It's a simple criterion that needs to be checked. And then once we're having that, we can link it back via this formula here. We can link the 2 asymptotic expansions and then get something out of that, because no error term here. We can transfer that to the other sequence as well. No need to compute the Fourier coefficients anymore because of this connection that just now mentioned, but let's see what the result is. It's like that here. So we again have an asymptotic result. That result is priorly known, but just we get it again out of our framework here, so to say. We have only the main term. As I mentioned, there is no error term. And as I said, by investigating this connection between the 2 sequences again, we can even say that this fluctuation is related to the fluctuation that we had on Stern's sequence before. So it's not only that the 2 sequences kind of share a connection, but also their asymptotics, which is indeed quite nice. And finally, as we have it here now without an error term, we can use this result together with the other result to get also a result here without error term for Stern's diatomic sequence. We slightly have to modify the summation and add here 1/2 of dfn. Doing that, the error term here vanishes and we get this result here. Okay, so that's basically what I wanted to tell you. So we have a framework for the k-recursive sequences. Once it falls under that, computations are much easier than in a general case for k-regular sequences. In particular, if I want to extract the asymptotic information out of the sequence, we simply have to consider these smaller matrices, which are easy to get, still have to do the computations of the joint spectral ratios, which sometimes can be hard, but still possible to do, and then get these kind of results out with a particular explicit knowledge of these fluctuations in terms of efficiently computable Fourier coefficients. And that's the end of my talk. Thank you very much.
Oh, thank you very much, Daniel. Does anyone have any questions? Yeah, Jeff has a question.
Yeah, I guess this is from both me and Jean-Paul simultaneously. Do you have some good, well, there's 2 questions. First one, do you have a good example of something that's k-regular but not k-recursive?
Actually, not right now. So I think we started discussing that at one point per email, I guess. So I still haven't dig much into that, but at the moment I don't have any example that that's the case, that these are really different. So yeah.
Okay, would Rudin Shapiro possibly be an example?
Maybe, not sure.
Okay.
Yeah, so but yeah, I will put that on my list additionally and check.
Christoph?
Yes, hello. Thank you for the nice talk. I think my question has to do also with the previous question. Assuming that the two classes are different, can you characterize the set of k-recursive sequences among the set of k-regular sequences?
Yeah, so actually at the moment that's not clear whether these two classes are really different or not, so I guess so, but still that's kind of follow-up work. And yeah, so I already started in thinking about that, but still no result present here.
Perhaps you can, you mentioned that there is some block form in the matrices. I did not quite understand what this means exactly, but I mean the exact what you mean exactly. And but this reminds me the concept of syntactic algebra. You know, the k-regular sequences are in some sense non-commutative rational power series, and there is a theory of syntactic algebras which could perhaps characterize the Ur class among the larger class of k-regular sequences. It could be so. You can look at my book with Berstel to know what is a syntactic algebra.
Yeah. So for sure, that would be interesting to know and to characterize. Yeah, I agree.
The block forms occur very frequently in syntactic algebras or linear representations.
Yeah, indeed. So, however, it turns out for the k-recursive sequence, these blocks seem to be much easier in some sense to write down explicitly. So
yes, but can you say you have? What I understood is there is some triangular block form, a block triangular form, what the examples you showed. And can you say something about the diagonal blocks? This would be my question.
Yeah, they are known explicitly. So you basically look at the paper and then there is an explicit formula.
Is there a paper published or somewhere?
Yes, it's already published. I can send the link in the chat, I guess. I hope that I find it quite fast.
I have just a last question. I saw in your formulas that sometimes there are minus signs, and would it be true that if your k-regular sequence is which I suppose to be k-recursive also, is it true that if there are only plus signs for the k-recursive structure, then you can also find only plus signs for the for your structure? This would be also it's a question which is very natural when you think to n rational series.
Yeah. Okay. Actually, so did not go into that. So that of course would be quite interesting to study. Yeah.
Just last word, because I speak too long. The idea is to get rid of the minus signs. Thank you.
Hold on, there's one more question. Gurnur.
Yeah, so thank you. First of all, thank you so much for the wonderful talk. And yeah, so I had the same question as Christoph, and thank you. Like, it has been answered. Thank you so much.
Okay, thank you. Jean-Paul had a question in the chat. He asked, how are k-recursive situated with respect to k-synchronized sequences?
Oh yeah, so that's also not clear at the moment. what the connection between these two is. So basically, there is at the moment where the k-recursive are located, it's not clear to me.
Yeah, any other questions?
Narad, if I may ask
Yeah.
one.
Yeah, go ahead.
So thanks, Daniel, for the nice talk. It was very nice. I have a question. So, I mean, thinking about, my papers, do you think your method could be generalized to, exotic regular sequences? Like when I say exotic, abstract numeration systems related.
Maybe, I'm not sure. So the maybe I know too little on the exotic numeration systems, but so I think at one point we need to be somehow in the complex numbers to get asymptotics out of that.
Okay.
I'm not sure how that is an issue for your numeration systems.
Yeah, I don't know.
But maybe, so probably we should just look into that at some point.
Yeah, because in that paper, I mean, the one with the generalized, I mean the asymptotics for the generalized Pascal triangle, there is another sequence related to, I mean, that we obtained from the Fibonacci enumeration system. So maybe this one is easier. I don't know. But in that case, I think if I remember well, we obtain an error. But I don't know if you're
I think it would be interesting to study kind of the combination of these things. So for the regular sequences here, so that's basically the standard k-area expansion is used. Could be that another numeration system is there, and what are the properties of these systems then? So not even going into asymptotics there, but just studying these linear representations and seeing what's there. Not sure, but what's there out already and what it could bring. So, but it for sure is interesting.
Okay, thanks.
I think so.
Thank you.
Any other questions? All right, if not, thank you very much, Daniel.